3-eye atlas offers a rare glimpse into the conditions of planetary formation far beyond our solar system. The fact is that the comet's composition, including ices, dust, and trace organics, appears remarkably pristine. Scientists note that these materials have likely remained largely unaltered for millions of years, preserving chemical signatures from the early stages of its home star system. Standard interpretations suggest Atlas may act as a natural time capsule, helping astronomers understand how planets form in environments unlike our own. One key insight comes from the comet's icy structure. The layered arrangement of volatile ices, interspersed with dust grains, reflects a history of accretion under low-temperature conditions. In many solar system comets, heating, collisions, or radiation have altered the original ice dust layers, but Atlas seems to have retained much of its primordial arrangement. Some researchers propose that studying this layering can reveal the relative timing of ice and dust accumulation, shedding light on early disk evolution. Yet the precision and preservation of the layers are somewhat unexpected. A few astronomers, speaking anonymously, speculate that the comet may have experienced unusual shielding during its interstellar journey, though no concrete evidence confirms this. Trace organic compounds in Atlas also provide important clues. Molecules, such as simple hydrocarbons and nitriles, appear in ratios different from those seen in solar system comets. Standard explanations suggest these differences reflect the chemical environment of a distant star system, possibly with unique metallicity or radiation exposure. However, some researchers note that the ratios are surprisingly consistent across different observational campaigns. In the scientific community, there is quiet speculation that this consistency could imply internal stabilization mechanisms, unknown environmental effects, or processes that preserve the material in ways we do not yet understand. Minor isotopic anomalies add another layer of intrigue. Preliminary studies suggest that carbon, nitrogen, and oxygen isotopes deviate slightly from solar system norms. Official interpretations attribute these variations to the natural diversity of star-forming regions, yet the pattern is uniform across the comet's surface, which is unusual. Some insiders quietly speculate that the isotopic signature could encode information about the early chemistry of Atlas's system, or, more provocatively, that the consistency hints at mechanisms beyond standard astrophysical expectations. Atlas is weak, but directional outgassing may also hold clues about its history. While typical cometary missions are influenced by sunlight, Atlas exhibits small jets of gas and dust that appear aligned along certain axes. Scientists suggest fissures or thermal channels could explain the behavior, yet a few astronomers, speaking anonymously, note that the pattern is strikingly regular. Could this reflect internal structural organization or some unknown effect of its interstellar travel? The available data cannot provide a definitive answer. Adding to the mystery are minor gaps in the datasets. Certain early spectroscopic readings and high-resolution images were temporarily restricted or delayed before public release. Official statements cite calibration and processing issues, but insiders hint that the raw data may have contained subtle chemical or structural anomalies. Why these datasets were smoothed or withheld remains unexplained, leaving room for speculation. Taken together, Atlas offers a unique window into the early stages of planetary formation, preserving icy layers, organics, and isotopic ratios from a distant system. While natural explanations are plausible, gaps in the data, unusual consistency in chemical and isotopic features, and subtle anomalies in structure and emissions invite curiosity. Whether Atlas is simply a pristine comet or a more enigmatic messenger from another star system remains unresolved. Its secret encourage both careful scientific study and imaginative speculation. One of the most compelling insights offered by 3I Atlas concerns the environment in which it formed. The fact is that analysis of its dust and ice composition suggests formation in a cold, outer region of a protoplanetary disk, far from its parent star. This inference comes from the dominance of carbon-rich ices and the relative scarcity of silicate minerals. Standard interpretations suggest that Atlas accreted in a region similar to our own Kuiper Belt or Oort cloud, where low temperatures allow volatile compounds to condense. Yet the exact ratios of carbon, nitrogen, and trace organics are unusual, prompting some researchers to question whether its birthplace was truly analogous to our solar system's outer reaches. Further evidence comes from the isotopic ratios of key elements. Carbon-12, carbon-13, nitrogen-14, nitrogen-15, and oxygen isotopes show patterns subtly different from solar system comets. Official explanations attribute these differences to natural variation among star-forming regions. However, a few astronomers, speaking anonymously, note that the ratios are unexpectedly uniform across Atlas's surface. Some speculate that this uniformity could imply long-term preservation of pristine material or even selective processes within the disk that favored certain isotopes. Why the ratios are so consistent remains an open question. Atlas's physical structure provides additional clues about its formation. Its small size, elongated shape, and remarkably low albedo suggest that the comet experienced minimal collisional evolution, preserving its primordial form. While typical comets in our system often show signs of fragmentation or surface erosion, Atlas seems unusually intact. Some researchers quietly speculate that this could be due to a rare protective environment, such as a disk with minimal gravitational perturbations, or perhaps exposure to unknown shielding effects during interstellar travel. The data allow multiple interpretations, leaving space for conjecture. Dust grain analysis adds another layer of intrigue. Fine carbon-rich particles dominate Atlas's composition, with a narrow-sized distribution that is atypical for comets in our solar system. Laboratory simulations suggest that such uniformity can occur under very controlled conditions, yet the natural processes producing these patterns in distant protoplanetary disks are not fully understood. A few anonymous scientists have suggested privately that this uniformity might hint at structural or environmental effects beyond current models, though there is no direct evidence to support artificial influence. Some observational anomalies further fuel speculation. Early high-resolution images and spectral measurements of Atlas were temporarily withheld or corrected before release. Officially, this was due to calibration and processing issues, but insiders hint that these datasets contain subtle features, minor chemical peaks, unusual dust alignments, or faint thermal variations that were initially smoothed or suppressed. Why these data were handled this way remains unexplained, leaving room for conjecture about hidden details in Atlas's formative history. Taken together, 3I Atlas provides a rare window into the early processes of protoplanetary disk formation. Its icy composition, isotopic uniformity, unusual dust characteristics, and intact structure suggest a complex history. While natural explanations are plausible, gaps in data and subtle anomalies leave room for speculation about environmental factors or processes not fully understood. Atlas remains a messenger from another star system, hinting at the mechanisms that shape planets long before they emerge. One of the most intriguing aspects of 3I Atlas is its inventory of organic molecules. The fact is that spectroscopic observations detected a range of simple hydrocarbons, nitriles, and possibly traces of more complex organics, although the data remain limited due to the object's distance and faintness. In standard interpretations, these compounds suggest that Atlas formed in an environment rich in carbon and nitrogen, where chemical reactions on ice grains created basic building blocks for more complex molecules. Yet the precise ratios and distributions are unlike those commonly observed in solar system comets, hinting at unique chemical conditions in its home system. The spatial distribution of these organics across Atlas's surface is another puzzle. Observations indicate that some molecules appear concentrated in certain regions rather than evenly dispersed. Standard models would predict relatively uniform deposition across a small comet over millions of years. Some researchers, speaking anonymously, suggest that the localized concentrations may imply internal reservoirs or channels, possibly preserving the compounds from degradation. Others speculate, more cautiously, that external processes during interstellar travel, such as cosmic ray exposure or magnetic interactions, could have selectively altered surface chemistry. Minor isotopic anomalies in the detected organics add further intrigue. Ratios of nitrogen, 15 to nitrogen, 14 and carbon, 13 to carbon, 12 differ slightly from those in solar system analogs. These variations may provide a window into the chemical environment of Atlas's birth region, or perhaps hint at processes not yet fully understood in astrochemistry. Some insiders whisper that the consistency of these isotopic ratios across multiple observations could suggest deliberate preservation mechanisms or even structural effects within the comet that protect the organics, though no direct evidence supports such a claim. Atlas's outgassing behavior during sublimation events also influences the chemistry. Certain jets release faint bursts of organics along with CO and water, but the composition appears unusually stable. Standard explanations attribute this to the comet's low activity and small size, allowing minimal chemical alteration. Yet a few astronomers have privately noted that the stability and repeatability of these emissions are striking. Could internal structures guide the volatile release in a controlled way, or is this simply a consequence of natural layering? The data leave the question open. Observation anomalies contribute to the mystery. Some spectral datasets initially showed faint, unidentified lines that were later removed or smoothed before public release. Official explanations cited noise and calibration artifacts, but insiders suggest that these lines could correspond to unusual organics or unexpected chemical compounds. Why these potential signatures were not highlighted publicly is unexplained, creating a subtle gap in the record that encourages speculation. Taken together, Atlas's organic chemistry presents a fascinating blend of the familiar and the enigmatic. Its hydrocarbons and nitriles, unusual isotopic ratios, localized distributions, and stable outgassing hint at complex processes that shaped the comet in its early system. Whether these patterns arose purely from natural chemical evolution or hint at unknown preservation mechanisms remains unresolved. Atlas carries whispers of the early chemistry of planets, offering scientists a rare glimpse into the building blocks that may have contributed to planetary formation far beyond our solar system. The structure of 3I Atlas offers another window into the early stages of planetary formation. The fact is that observations reveal multiple layers of ice interspersed with dust, creating a stratified composition rarely seen in comets from our own solar system. Standard interpretations suggest that these layers formed as the comet accreted material from a cold protoplanetary disk, with each layer representing a distinct period of ice and dust accumulation. This layering could provide insight into the timing and dynamics of planetesimal formation in Atlas's home system. Yet the degree of preservation is striking, even for a small interstellar object traveling for millions of years. Thermal measurements add to the puzzle. Certain regions of Atlas's surface retain colder temperatures than expected, suggesting insulation by dust layers or low thermal conductivity. In standard models, uneven heating would gradually alter the ice layering, but Atlas shows minimal surface alteration. Some researchers, speaking anonymously, speculate that the layering may be unusually dense, or that internal structures protect the ice from cosmic rays and interstellar radiation. Why the layers remain so intact over time is still unclear, leaving room for interpretation. The isotopic composition within these layers also carries subtle anomalies. While oxygen, carbon, and nitrogen isotopes roughly align with expectations for a distant protoplanetary environment, some ratios are surprisingly uniform throughout the comet. Standard explanations point to selective condensation in the early disk, but a few astronomers quietly suggest that the uniformity could imply internal stabilization or preservation mechanisms. Could interstellar travel have further homogenized the layers? Or does the comet's formation environment naturally produce such regularity? No definitive answer exists. Outgassing from the stratified layers provides additional clues. Jets of gas and dust emerge from fissures or vents, releasing materials in bursts that reflect the underlying layering. While scientists attribute these emissions to thermal sublimation of volatiles, certain jets appear unusually coherent and consistent over multiple observations. Some insiders whisper that this behavior could hint at internal channels or structural organization guiding the flow of gases, though evidence for such structures is purely speculative. The regularity of the emissions contrasts with the chaotic behavior observed in many solar system comets. Observation anomalies add to the intrigue. Early high-resolution imaging of Atlas's ice layers was temporarily withheld or adjusted before public release. Official explanations cite calibration or processing corrections, but insiders hint that the original data contained subtle structural features, thin ice strata, unusual fissures, or fine layering that were partially smoothed. Why these details were not fully shared remains unexplained, feeding speculation about hidden complexity in the comet's interior. Taken together, Atlas's layered structure, thermal patterns, isotopic uniformity, and coherent outgassing paint a portrait of a small but remarkably preserved interstellar object. Its stratified ices may offer a unique record of planet-forming processes in a distant system. While natural explanations are plausible, gaps in the data and subtle anomalies leave room for curiosity and speculation. Atlas acts as a frozen archive, holding whispers of planetary histories that existed long before its journey toward our solar system. The full story remains just out of reach, encouraging both scientific inquiry and imaginative exploration. 3I Atlas provides valuable clues about the dust grains that contribute to planetary formation. The fact is that spectroscopic and photometric measurements detected fine, carbon-rich particles embedded in its icy matrix. These grains are relatively uniform in size and composition, unlike many solar system comets, where dust shows broader size distributions and varied chemical signatures. Standard interpretations suggest that Atlas formed in a region of its protoplanetary disk, where dust coagulation was steady and undisturbed, allowing for the creation of uniform grains over long timescales. The physical properties of these dust grains also offer subtle insights. Their low reflectivity and consistent composition suggest a high carbon content with minimal contamination from silicates or metals. In standard models, this points to a cold, outer disk environment with limited thermal processing. However, some researchers, speaking anonymously, note that the degree of uniformity is unusually high for a natural process. Could there have been stabilizing mechanisms in Atlas's birthplace that favored specific grain sizes or compositions? The data do not provide a clear answer, but the pattern invites speculation. Isotopic analysis of dust adds further intrigue. Ratios of carbon 12 to carbon 13 as well as nitrogen isotopes, differ slightly from typical solar system values. These anomalies may reflect the unique chemistry of the star-forming region where Atlas originated, or they could indicate preservation of primordial materials unaffected by thermal or radiative processing. A few insiders suggest privately that the isotopic consistency across multiple dust grains might hint at unusual environmental conditions, or even processes that selectively protected these grains during interstellar travel. The interaction between dust and gas emissions in Atlas is another subtle feature. Observations indicate that dust particles are often ejected along narrow, well-defined jets, closely associated with CO and minor water outgassing. Standard interpretations attribute this to the orientation of fissures and localized heating, but the precision and coherence of these jets have raised eyebrows among a few astronomers. Some quietly speculate that internal channels or structures may guide the dust release, though no evidence supports this beyond circumstantial patterns. The repeated observation of similar jet orientations over time strengthens the curiosity without providing conclusions. Observation gaps contribute to the mystery. Early high-resolution images and dust spectra were temporarily withheld, and certain datasets were later smoothed before public release. Official explanations cite noise reduction or calibration, but anonymous sources hint that the raw data may have contained minor anomalies in particle alignment or unusual chemical signatures. Why these observations were edited remains unexplained, leaving an information gap that encourages speculation about hidden features in the comet's dust environment. Taken together, the dust grains in Atlas offer a rare glimpse into the primordial building blocks of planets. Their uniform size, high carbon content, isotopic anomalies, and coherent ejection patterns suggest both familiar and enigmatic processes at play. While natural explanations, including slow coagulation in a quiet protoplanetary disk, are plausible, subtle anomalies and gaps in the data leave room for conjecture. Atlas may serve as a cosmic archive, revealing secrets of planet formation that have traveled across interstellar space, still holding mysteries beyond our current understanding. The volatile compounds of 3I Atlas offer critical insights into the conditions of planetary formation in distant star systems. The fact is that the comet's composition includes water ice, carbon monoxide, carbon dioxide, and trace organics, all detected via spectroscopic observations during its passage through the inner solar system. These volatiles reflect formation in a cold region of a protoplanetary disk, where ices could condense and survive over millions of years. Standard interpretations suggest that studying these materials can inform scientists about the types of compounds available for building planets and the potential for prebiotic chemistry in other systems. The ratio of volatiles in Atlas is unusual. Carbon monoxide appears relatively abundant compared to water ice, more so than typically observed in solar system comets. In conventional explanations, this could result from formation at very low temperatures far from the parent star, where CO condensation dominates. Yet some researchers, speaking anonymously, note that the relative stability of these ratios throughout observations is striking. Could there have been stabilizing processes within the comet, or is this merely an unusual but natural variation? The data are suggestive but not definitive. Isotopic anomalies in these volatiles add further intrigue. Preliminary measurements of oxygen, carbon, and nitrogen isotopes differ subtly from the expected norms for solar system materials. Standard interpretations point to environmental variation in the comet's birth region, but some insiders quietly suggest that the uniformity of these anomalies across multiple measurements might hint at unknown preservation mechanisms. Whether these isotopes reflect unique chemical conditions or hidden physical processes remains uncertain. Outgassing behavior also provides insight into the comet's history. Atlas releases volatiles in discrete jets, often aligned with specific fissures or surface features. Standard explanations attribute these patterns to solar heating and the comet's rotation, yet the coherence and regularity of some jets are unusual. A few researchers, speaking privately, speculate that internal channels or layering may guide the gas flow in a controlled manner, a possibility not fully considered in conventional models. The observations leave space for alternative interpretations. Observation gaps contribute to the mystery. During periods when Atlas approached its closest point to the Sun, some high-resolution spectroscopic data were unavailable or delayed, officially due to instrument calibration or limited visibility. Anonymous sources suggest that these missing datasets might have captured transient chemical emissions or subtle anomalies in gas composition. Why this information was restricted is unexplained, leaving room for speculation about hidden features in Atlas's volatile behavior. Taken together, the volatile compounds of Atlas provide a rare window into the chemistry of planet-forming regions beyond our solar system. Water, CO, CO2, and trace organics, combined with isotopic patterns and jet behaviors, reveal both expected and enigmatic properties. While natural explanations involving cold formation and preservation are plausible, gaps in the data and subtle anomalies leave space for curiosity and conjecture. Atlas's gases may hold secrets about how planets form, the chemical environment of distant disks, and the primordial building blocks that could support life elsewhere. The full story remains just beyond reach, inviting both scientific inquiry and imaginative interpretation. 3I Atlas allows astronomers to compare planetary formation processes in different star systems. The fact is that its composition, isotopic ratios, and structural properties differ subtly from comets observed in our solar system. For example, its higher carbon-to-oxygen ratio and unusual isotopic uniformity suggest formation in a disk environment distinct from that of our Sun. Standard interpretations hold that these differences can reveal the diversity of planetary formation processes across the galaxy, offering a broader perspective on how planets and minor bodies emerge. Dust and ice layering provides additional comparative insights. Atlas's well-preserved stratification is uncommon even among solar system comets, where collisions, heating, and radiation often erase early formation features. Some researchers suggest this may indicate that its parent system had a particularly quiescent outer disk, allowing material to accumulate slowly and remain largely intact. Others, speaking anonymously, note that the consistency of layering may hint at unknown stabilizing mechanisms, possibly related to the comet's interstellar journey, though no direct evidence confirms this. Volatile content in Atlas also contrasts with local comets. Its relatively high proportion of carbon monoxide and consistent minor organic emissions suggest formation in extremely cold, chemically unique regions. Standard explanations attribute this to disk conditions and low stellar irradiation. However, some insiders quietly speculate that these volatiles' unusual stability could hint at processes beyond natural expectations, such as shielding from radiation or even internal structural effects that preserve delicate ices. The observations are inconclusive, leaving room for interpretation. Isotopic patterns provide further comparative clues. Ratios of carbon, 12 to carbon, 13, nitrogen, 14 to nitrogen, 15, and oxygen isotopes show subtle deviations from typical solar system comets. Official explanations focus on natural variation among star-forming regions. Yet a few astronomers, speaking privately, point out that the uniformity across Atlas's surface is striking, possibly indicating selective preservation of primordial material. Could these isotopic consistencies reflect unknown cosmic effects or rare formation conditions. The data are suggestive, but do not resolve the question. Observation anomalies also fuel speculation. During periods of closest approach, some high-resolution spectra and images were temporarily withheld or smoothed before public release. Officially, this was due to calibration or processing issues. Anonymous insiders suggest that these gaps may have concealed minor compositional anomalies or unusual structural features relevant to understanding planetary formation. Why this data was restricted remains unexplained, leaving space for conjecture about hidden information in Atlas's comparative record. Taken together, Atlas provides a unique laboratory for understanding how planetary systems form beyond our Sun. Its dust, ice, volatiles, isotopes, and structural preservation offer both familiar and enigmatic clues about the processes shaping planets. While conventional models explain much of the comet's composition, subtle anomalies and gaps in the data encourage speculation about unknown mechanisms or environmental factors. Comparing Atlas to solar system comets expands our perspective on planetary formation, revealing the rich diversity of outcomes in the galaxy. Its story is a puzzle still being pieced together, hinting at the broader mysteries of cosmic evolution. 3i Atlas offers a rare opportunity to look back at the processes that shaped planetary systems long before our solar system existed. The fact is that its composition, structure, and isotopic signatures preserve clues from its formation environment, possibly billions of years ago. Standard interpretations suggest that studying these features can help scientists reconstruct the conditions of protoplanetary disks and the early chemistry of planets in distant star systems. Yet several aspects of Atlas remain enigmatic, leaving room for both scientific curiosity and speculative interpretation. The comet's layered ice and dust provide a natural record of its early environment. Observations show distinct strata, indicating periods of accretion under relatively stable conditions. In typical solar system comets, collisions, heating, or radiation often disrupt these layers, but Atlas appears remarkably preserved. Some researchers, speaking anonymously, suggest that this may indicate a particularly calm formation region or unusual shielding mechanisms during interstellar travel. Others speculate that the layering itself could encode subtle information about the timing of planetesimal formation, though no definitive pattern has yet been confirmed. Atlas's volatile composition also provides temporal clues. Water ice, carbon monoxide, carbon dioxide, and minor organics remain in proportions that reflect formation in a cold outer disk. Standard models suggest that such compositions freeze in the chemical environment of a young star system, effectively locking in a record of early planetary chemistry. Yet certain jets of outgassing appear unusually consistent over time, leading some insiders to quietly speculate that internal channels or structures may preserve volatiles in ways not fully understood. Could these patterns hint at processes beyond natural evolution, or are they simply the result of fortuitous preservation? The observations leave the question unresolved. Isotopic ratios add another layer of intrigue. Measurements of carbon, nitrogen, and oxygen isotopes reveal subtle deviations from solar system norms, while maintaining remarkable uniformity across Atlas's surface. Official explanations attribute this to the natural diversity of star-forming regions, yet a few astronomers note privately that such uniformity is striking and potentially unexpected. Some speculate that it could indicate selective preservation of primordial material or unique conditions in Atlas's birthplace, though evidence remains circumstantial. Gaps in observational data contribute to the sense of mystery. High-resolution images and spectral measurements were temporarily restricted or later adjusted before public release. Official statements cite calibration, noise reduction, or processing corrections. But anonymous sources hint that these datasets may have contained subtle structural features, unusual chemical lines, or minor isotopic anomalies. Why these details were smoothed or withheld remains unexplained, leaving room for conjecture. Taken together, 3I Atlas acts as a cosmic time machine, carrying whispers of distant planetary formation and chemical evolution. Its layers, volatiles, organics, and isotopic signatures provide a preserved record of a star system far beyond our own. While natural explanations for its properties are plausible, subtle anomalies, observational gaps, and unusual consistencies invite curiosity and speculation. Atlas reminds us that interstellar objects can serve as messengers from the distant past, offering glimpses into the processes that shaped planets long before humanity looked up at the stars. Whether the story it tells is fully natural or contains hints of deeper mysteries remains a puzzle waiting to be unraveled.